next keynote address is Cyber Resilience and Energy Security. Our speaker is Erfan Ibrahim. He is the Center Director for Cyber Physical System Security and Resilience R&D at the National Renewable Energy Lab. Ibrahim works with public and private sectors, identifying security requirements, evaluating cybersecurity standards, testing cybersecurity controls, and determining residual risk in smart networks. Thank you.
Good morning. I'm here to talk about how to securely integrate distributed energy resources to the grid. It's not as simple as just plugging it in electrically and making it work. So this is the culmination of research work at NREL that I've been leading for the last 2 years. And I think you're going to be pleased with what you see. So I'll provide an overview of our center and then talk a little bit about some of the challenges of distributed generation from a cyber perspective, a reliability perspective, as well as a carbon footprint perspective. And then I'll talk about what a utility in the future could do and how it could fit into this new energy economy. And then if we have a minute left after that, we could have a Q&A. My background, as you can see, I have a PhD in nuclear engineering, and then I have worked over the last 22 years in information technology, cybersecurity, communications. I used to manage the western backbone of the internet in the mid-90s for Pacific Bell, which is now AT&T. So I have a lot of hands-on operational experience working large networks. And then I've also worked in water. I've advised the government of United Arab Emirates on desalination, and I have some interesting techniques for cleaning water. The team that I have at NREL is quite diverse. We have people in power systems, in communications, networking, and they come from various backgrounds. And that collectively allows us to look at the problem in a systemic fashion. Our strategy is very simple at the National Renewable Energy Lab in my center. We try to work with the private sector, identify the gaps by working with them, inform the agencies that fund R&D to address those gaps, rather than sit in some ivory tower and postulate on what's needed. We work with the private sector and then actually work on those research projects that are funded. Our expertise in SCADA, in cyber, and communications allows us to look at the problem of connecting renewable energy, batteries, and other things to the grid in a holistic fashion, and that is really needed. And we've built a user facility at NREL where you can come in and test things out on our infrastructure. And that's a critical thing to go from theory to practice. In order to reduce the commercial risk, you have to do experiments. And you can't just do risk analysis and then go deploy. You have to solve the engineering problems. There are a lot of kinks, as you will see. This is our facility. I'm sure many of you have come down the hill and seen it. And we are in this Energy Systems and Integration facility. We have 3 parts to our building: an administrative part, a high-performance computation center that has 2.25 petaflops of computational capacity. That's to the power 15. So that's a lot of crunching capability. And we use it like a restaurant where you come in, you get a table for a little while, we feed you, and then out you go. So it's like a rental facility of computation. It allows us to simulate the entire grid if we wanted to of the United States, not a problem. And then we have purpose-built labs in the back, as you can see. Our cyber lab is in the systems performance lab, And we have purpose-built labs with a megawatt of power capability connection. There are 4 lines, 2 AC and 2 DC, each 250 kilowatts. So we can connect different labs electrically and run experiments. And that's a key feature of our energy systems integration facility. It's very hard. You can't use the wall wire if you're running kilowatts of power. So that's why you need this research distribution bus. So what's the challenge with renewable energy? People are talking about how it's connected to national security. Well, you don't want it to become the Achilles heel of national security. So let me explain to you what the problem is. You got centralized generation. You got big power plants. So there are very few players in the market. You get on the phone, you talk to them, you can maintain a consistent cybersecurity posture across the sector. Now look what's happening. You got wind, you got solar, you got batteries. Now you'd think, oh, this is all helping in lowering the carbon footprint. But think again. Every single one of those devices is an attack surface for a cyber attack. And by the way, these are not untrusted systems. If you're going to connect these electrically to the grid, guess what? These are trusted nodes. So all those IT-centric credentials they keep talking about, blockchain, encryption, none of that will work. When you give physical access, and I can break these systems, and I can attack the grid backwards. So none of that stuff that you're hearing from securing these things works. Because they're trusted systems that get compromised by hackers who know how to break into them. You can change the firmware. When you have physical access, you can do things. So keep that in mind as we're making this paradigm shift. Now let me give you something that you'll lose sleep over for the next few days. As if the last slide wasn't bad, look at this. So I have physical access as a hacker. I now start exploring what else is on the network. I figure out the vulnerabilities. I design malware that suits the vulnerability, and I launch an attack backwards to the operational center. I can completely do this. No problem, because it's part of the SCADA system. Look what I do. I shut off the substation. Black energy in reverse. Ukraine, backwards. I'm hitting from the field to the substation. I'm not coming from the internet. Forget that. That's yesterday's news. Now, I go to the IT side, and I start exfiltrating data. Checkmate. Like it? Coming to a theater near you. The larger the energy mix of distributed energy resources, the more this is going to happen. And there's nothing you can do about it with the way we are doing security today. And that's why I'm here. Remember, I said there will be good news at the end. It's the first thing you do. You scare people, then you tell them the good news. I'm giving you sneak previews of coming attractions. So now we look at all this energy infrastructure with all these smart grid applications coming on across a wide ecosystem. There are threats galore. I mean, it's a target-rich area for hackers. And hackers are brilliant people. They just misunderstood. Nobody played with them in the sandbox. Nobody had lunches with them in elementary and middle schools. They're misunderstood. So they're trying to prove themselves. We should give them some to prove themselves, but not everything. And that's the basis of my architecture. So look at the traditional approach to security. It's all about encryption, 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 a bunch of endpoint security like blockchain and things like that. The problem with that approach is it's too heavy, the legacy equipment becomes obsolete day one, and you're always playing catch-up to the hacker because by the time you certify stuff and put it out there, the threat vector has moved. Now, let's look at the NREL approach. The NREL approach says, keep the power system as is. Don't worry about it. But dress it up with purpose-built cybersecurity technologies that do very specific things. Inline blocking and intrusion detection. They understand the transactions. and they don't allow certain transactions. They block them. If you put that in the power systems, it's like locking your house and putting the keys on the front door. What do you think the first thing a hacker is going to do when they attack a power system? Shut off the cybersecurity controls of the power systems. What an oxymoron. And billions of dollars are being wasted in shoving security into the power systems, when that's the first thing they're going to shut off when they have physical access to the devices. I just showed you the scenario. I just don't get it. So the NREL approach is design the network properly to build natural immunity in it. Don't move data unless there's a need. And whatever residual risk is left, put purpose-built cybersecurity technologies, intrusion detection and inline blocking, to just stop this hacker from getting around. I've proven it empirically. We've run 5 use cases on the test bed we built that work for distribution utilities. Those are listed there. And we attacked it while we were running use cases to see if this architecture actually holds. And we brought in 2 sets of pen testers who work with defense and intelligence over a course of 12 months. And they shook their head and said, when we are outside, we can't get in. When you put us inside, we can't go anywhere. We don't like this. I said, this is great. Because all you want to do is create disincentives for hackers. So here's the network. As you can see, I've got a work control center and 2 substations. I've got a segmented network. I have IT, OT, and management as separate VLANs. OT means operational technology, where the SCADA runs. Management is where I control all the devices from the back end. So when a hacker hits my network, they don't even know I'm watching them. They don't know I'm blocking them. They can't do denial of service attacks. So I've had a gig speed attacks on my SCADA system. You see those blue boxes? They have Windows running on them. They're SCADA systems with Windows. I mean, Windows and security can never be used in the same sentence. It's not grammatical. But by putting inline blocking tools like Blackridge and SecLab and intrusion detection systems like NDimension and Albedo and Next Defense, I'm able to checkmate the hacker from any angle. They come from the field, I'll block them with my inline blocking. If they come in from outside, my access control lists on the firewalls and the switches block them. It's so frustrating for the hacker. So this is kind of like Kellogg's cornflakes. Taste it again for the first time. What happened to common sense in designing networks? It's just out the door. Moore's law has intoxicated people to the point where they're just shoving bits because they can. Who says you have to move traffic just because you can? Quiet down the network. Block. Allow only traffic to move when there's a reason. So when an anomaly occurs like a hack, it's a new use case. You're like, no, I don't accept this use case. You're not getting anywhere. That's the way to protect systems. Not by putting a lot of encryption and authentication technologies in the system itself, having them be shut off, and then have free reign over the whole infrastructure the way we design today. It's very unfortunate. So here are all the products that show how I protect all the logical layers of the testbed. And you can see all the 7 layers of OSI, the semantic and the business process layer are being protected. These are off-the-shelf products, by the way. They're commercially available. So where was the research needed? In the integration of the products to create a holistic security posture. That's where the creativity is needed. Good network design, good hygiene, and purpose-built products that do that. Now, as the threat changes, I just change out the cyber products. I don't have to change the power system. Remember, it costs billions of dollars to upgrade a power systems, and cyber is a very small part of it. Why would you want to? That's like wagging the dog. You don't do that. Okay, so here's the electrical picture, and you can see that I'm connected to actual distributed energy resources, a grid simulation, and a SCADA system. So I have an end-to-end distribution utility and renewable energy in my lab. Come sometime, I'll show it to you. If you're not a US citizen, it takes 2 weeks. Now, this is what I want to leave you with. We have a 10-step process for securing enterprises. I call it the systems engineering approach to securing. The first thing you do is you do a cyber governance assessment. The next thing you do is you figure out where the gaps are and develop a technical implementation plan to realize those gaps, fill them. And then you do the due diligence on the technology that support that gap filling. Then you develop the procurement language to get those products because you know what the requirements are. Then you do the 9-layer review to make sure there are no gaps left. And then you scan all the softwares. Don't rely on supply chain risk management. It makes lots of money for companies like Deloitte, but it's all conjecture. Data fuzz testing. You have to do this. This is what hackers look for. And then you pen test it in a system, because until you don't do that, you don't know if you've dealt with the residual risk. Then you look at all the ways you can fail a system and try to develop mitigations for it. That's how you build resilience in a system. And finally, you train your people on all the changes you've made. This is a 10-step process called a system engineering process. So I hope that these slides are going to be available to you. But what I want to do is, these are the controls in the governance assessment. I'll just take one more minute to talk about this. This is the duck curve. And what you don't want is to be pate in this business. Okay? What I'm talking about here is that the more renewable energy we get in the middle of the day, the worse it is from a utility perspective, because the duck keeps getting skinnier and skinnier. So what you have to do is ways of fattening this duck. One way is to use some of that excess power that you have to desalinate water, to clean brackish water. That will fatten the duck. You don't need to put it in expensive chemical-based storage units. Why? Salt water conversion to fresh water is a type of energy storage. So look into that. You want to reduce the carbon footprint of the supply chain of renewable energy so that you're not reducing carbon by adding carbon. So that's why I asked the question yesterday. We really need to look at that. And then, what should we do from a reliability perspective? I think the utilities should get involved in the renewable energy business because they have low cost of capital. So they can invest. They can rent out rooftops of people's homes. Arizona Public Service is doing that. They pay them $30 a month. And that way, the consumer doesn't incur the cost of financing solar panels, and yet they have clean energy being put into the system. So we need to have that ability. And then also, recycling is very important, applying demand response to align consumption when there is renewable energy available. And hydrogen is a big thing. I'll speak to you offline about that. So these are some of the strategic goals. I'm going to leave it like this. Could we get a minute to ask questions real quick? All right. So then in that case, I'm going to take you here because I'd like you to email me. I'm doing a lot of work in sustainability to build resilience in the systems. Resilience doesn't come just by putting cyber technologies. So with that, thank you very much.